Good morning, everyone. My name is Kishore. The topic is adiabatic process. The process in which the system undergoes a physical change in such a way that its heat energy remains constant is called adiabatic process. In which the system undergoes a physical change in such a way then its heat energy remains constant. Then this process is called adiabatic process. Let us derive the adiabatic process. The process in which the system undergoes a physical change. The process in which the system undergoes a physical change in such a way that its heat energy remains constant, then it is said to be adiabatic process. For adiabatic process, the system Boyle's law does not hold good. So, pressure and volume are constant. PV equals to constant. Heat energy Q is also constant. As here said above, heat energy remains constant. Heat energy Q equals to constant. The change in heat energy dQ is equal to 0. To carry out adiabatic process, the system must have insulating walls and the gas molecules in the system allowed to expand or compress suddenly. The gas which is used in adiabatic process is ideal gas, which is enclosed in a cylinder. Therefore, work done in adiabatic process. Let us consider 1 mole of gas, ideal gas, which is enclosed with a cylinder, enclosed in a cylinder and expand adiabatically. The total work done in adiabatic process is W equals to area of ABCD. Here ABCD means pressure on y-axis and volume on x-axis. As we know, when the cylinder is enclosed, the pressure decreased and volume increased. Expanded, pressure decreased and volume increased. As the cylinder is compressed, then the pressure is increased and volume is decreased. As we show here, shown as this is expanded. We showed P1 V1. Here compressed, B of P2 V2. Here P1 is less, volume is more. Here pressure is more, volume is less in when compression. In expansion, here W is equals to integral V1 tends to V2, dW is equals to integration V1 tends to V2 P dV. That we can say that this is equation 1. Then here PV equals to constant. Constant can be shown in K. Therefore, PVV equals to constant K. Then P is equals to VV by K. Let it be second equation. Let it be 2. P is equals to K by V power V. Let it be second equation. As we know that substitute equation 2 in equation 1, we get W equals to integration V1 tends to V2 K by V power V into dV. Here P value is K by VV. So it equals to K integration V1 tends to V2 to 1 by V power V into dV is equals to K integration 1 tends to V2 v power minus v into dv. 1 is equals to k into v power minus v by minus v plus 1. Here also plus 1. Therefore v2 tends to v1. As now w is equals to k by 1 minus v into v2 power minus v plus 1 minus v1 minus v plus 1. Okay. Now w is equals to 1 by 1 minus v into k v2 minus v power plus 1 minus k v2 minus v plus 1. Let it be third equation. According to adiabatic relation for initial coordinates p1 v1 power v equals to k, final coordinates are v1 v2 v is equals to k. By substitution above relation in equation 3, then w equals to 1 minus v into k v2 power minus v plus 1 minus k v1 minus v plus 1. Let it be third equation as we know. Now substituting, w is equals to 1 minus v into p2 v2 v2 minus v plus 1 minus k p1 v1 v minus v plus 1. Now w is equals to 1 minus v by into p2 v2 v minus v plus 1, here v cancel, minus p2 v2 v minus v plus 1 v cancel. W is equals to 1 minus v by p2 v2 minus p1 v1. Let it be fourth equation. As power 1 means 1. For ideal gas, p1 v1 is equals to RT1, p2 v2 equals to RT2. These two are equation 5. Substituting equation 5 in equation 4, w is equals to 1 by 1 minus v into RT2 minus RT1. For n moles of gas, w is equals to nr by 1 minus v into T2 minus T1. This is adiabatic expression for n moles of gas.